Just let me make some clarifications before starting. First, you received a link with a folder with some materials. Basically, we have some data there, and we have some code that we will be using in, let's say, half an hour maybe. So please download that folder into your computers and have it ready, because as Bestin said, now I'm working here in the Center for Demographic Studies in Barcelona in a project, an ERC project called Co-Residence, which aims to study family changes across the world since more or less 1970 till these days. We are using data coming from different data sources like IPUNS, DHS surveys, LFS, labor force surveys, the SILCs, and also we have some particular surveys for countries we are not covered in these repositories, like for Korea. Also, we are working with the Chinese family panel study, so huge amount of data. And this was the motivation for this presentation. I won't talk about the co-residence database hopefully in the next 6 months. You will start seeing a lot of articles coming from that. But because I'm here in charge of building this unexistent database of family changes across the world, I needed to develop some sort of our strategy of how to deal with this huge amount of data. Now imagine that nowadays the co-residence database is composed by 200 million registers, so one row, one person. All these data sources allow us to reconstruct households, so we know these 4 or 5 people live in this household, these other 3 people live in other household, and we needed to deal on how to compute the number of indicators that compose the co-residence database and how to deal with these tons of data in some sort of an efficient way. And because of some previous work I did in Geneva with Philippe Banner, working with the structural survey of Switzerland, in which we needed to follow people over time, well, I start getting familiar with what is to work with lists in R. So today I will give some insights, or I will explain why I think it's useful to be familiar with working with lists in R. And basically, I always think that when we talk about these R group meetings, it's always nice to showcase some sort of example of what we are talking, because if not, it's so much technical things. So first of all, I would like to know, and you can manifest this on the chat or by talking, how many of you work with lists in R, or have been working with lists, or are familiar with lists in R? You, David? Yes, I do also. Okay, so more or less, we have an idea of what we are talking about. So let me share my screen so I can move to my presentation. Okay. Remove this. So you see my presentation now, okay? Okay, so I entitled this Unravelling the Power of Lists in R. And as part of the motivation, that I was before explaining my personal motivation right now of building this co-residence database, but in general, we can say that every time that you need to work iteratively over a set of data frames or different object types, the for loops would be messy and difficult to read, and more sure not very elegant in how we write our code. For loops are great for starting automating a process of working with big data, big data sets. But if we want to scale this automation process to process more or larger files, well, I think it's convenient to be familiar with the apply family of functions in R. And today, I will be basically concerned about the lapply function, which is the one that we will use over list objects. But here, and I will send later today the presentation to Vestin so you can have the slides. I also put two different articles that I find interesting to read in case you are not familiar with this apply family of functions in R. So basically, these lapply functions will return a list of the same length as X, where X is always a list object, in which each of the elements will be the result of applying some sort of function to each of the elements of this list. And why do we want to master list and the lapply function? Well, personally, I think that working with list objects and using the lapply function will make our code more expressive, and in that sense, much more easy to read, to follow, and in case needed, to correct. No? So that's, let's say, the general motivation. Okay. Basically, a list object, you told me you are familiar, but this is this versatile data structure that can contain a collection of elements of a different type. No? In R, we are familiar that we have numeric vectors, so that means that all elements of that vector will be numbers. We have character vectors, which means all elements of that vector will be characters. And then we have more complex data objects like data frames or spatial objects. And the advantage of the list is that it will allow us to work with heterogeneous data elements within a single object. No? And as you can see in this scheme, within a list, we can group, for example, vector, matrices, arrays, data frame, and this is an aggregation of me because it was not on the original image, but we can also work with spatial objects as being part of an element of that list. No? So basically, if we want to create a list in R, we will use the function list, and here you have an example where we create three different elements, being a numeric vector of 1 to 4, a data frame with 2 columns and 3 rows, and a character vector with a single element being hello. And we can create a list by putting together these 3 elements. And if we call them this list, we will receive this structure that you see at the bottom of the slide, where it will tell you using an index like 1, 2, 3, because of the elements of that list, what it contains. No, nothing more than that. So we can also name the elements or the components of our list using the function names, and this will be useful to call or to extract the components of this list later when we need them. No? So if we apply names over a list called, in this case, list 1, and we equal this to numbers, some data, and letters, then instead of having the index in each of the elements, now we have these names. I found today that this can also be done directly by using this combination of table, double points, list, and setting the names. I read about this morning in a tweet. So, okay, once we are in front of the list, I found with some colleagues here that for people who are already working in R and they have some sort of proficiency in R, they have kind of difficult times to understanding how to access the different elements of the list. No? And here we have different strategies for accessing this. The more common way would be to use this double square bracket structure and basically calling the elements of the list by their index. No? And you need to notice that this double square bracket, because if you use just one square bracket, R will retrieve the element you are calling, but it will retrieve it as a list. No, so it won't show us the original data structure of that component. So in the previous, following with the previous example, if we call the third element of our list 1, we will receive the character vector hello. And if we call the element 3, but using just a single pair of a square bracket, we will receive the element hello, but still being a list. No? So this could be messy sometimes in order to work with them. So once we have named our objects of a list, we can also call it directly using this structure like base R, no, with the dollar symbol and calling the object by its name. Or, as we saw before, we can use the double square bracket and the name. So this will be the ways in we can access these different elements that we have inside. Also, once we are in the mindset of working with lists, we will also be aware that we can perform different tasks as in general we do with a single data frame. No? So imagine that we have this list of 3 elements, but by any chance we are only interested in working with the element 1 and the element 3, we can use this combination of the list and the C function, the concatenator function, telling R that we want to get the first and the third element of this list. And we will also be able to add a new component to this list using the dollar symbol, like using base R. And for example, in this case, in this example, they are adding a new component, which is basically the result of the linear regression. No? So nothing more than that. Also important when lists become long, no, let's say with a lot of elements, well, it's important to be aware that in case you want to delete one of the elements of this list, you can use an expression as simple as a list dollar symbol, the name of the element that you want to delete, and basically equal that to null. So this will take that element out of your list. So coming to the lap-like function, I said before that this will retrieve us a new list object of the same length of the list that we were using after applying some sort of function. And so here I have this scheme of what I call the atomic structure, no, of how to work with Laplace. So we will create a new object called new list. My new list will be equal to Laplace over my old list. And then in the function, of course, you can define whatever you want. And here I keep it very simple to define df telling the data frame, because I was thinking about working in a list with data frame. And then it's as easy as understand that whatever you define in the corpus of this structure is like working with a single data frame, but it will perform this operation over all the elements of the list that you are working with. And so, believe me, this will save you tons of lines of code and time. No? So in a moment, we will put hands on this and we will see, but I also want to state that once that we are working with lists, of course, we can also combine different lists. No? So imagine the case, and this is my case because I'm a spatial demographer, so I work a lot with statistical data, and I also need spatial data. So I have data, statistical data for different years, and in particular, when you work with the small spatial areas as census tracts, this change the number 1 year to other year. So you don't use just a single shapefile for all the data you have. Maybe you need also 3, 4, 5, or the same number of shapefiles as data that you are using. No? And the list will also allow us to combine iteratively elements of two different lists. No? So basically using the family of map functions coming from the library pur, you will be able to connect elements of different lists. Basically, this will proceed as matching them by their index. So it will take the first element of list A and will perform whatever task you're asking with the first element of list B, no, and so on and so forth. So this is, for me, really simple structures that will help you and will save you a lot of time and will improve your capability to manipulate, process data, and create visualizations at once, avoiding getting into for loops, which I truly find messy, let's say. So, as Diogenes says, this movement is demonstrated by walking. So now I will show you with the code 3 different examples of which I think that will help you to have a feeling of what you can do using lists. No, so first I will show you an example about, this is coming from my ongoing research. No, we need one of course of the indicators of the co-residence database is the average household size. And as I told you, I'm working with 200 million cases. I need to group these people into households. Then I need to group these households into countries, and finally get my indicator. So we will create some toy data to perform one of these examples. Second, I think this will be more. This is more. You will like more the second example. I will show you how to use list and the Laplace function for producing multiple ggplots and saving them. Now imagine this situation where you are making some sort of a study. It was my case during my PhD, about immigrant population in the different regions of Spain. And by any chance, you want to create a graph with the evolution of the foreign-born population and the Spanish-born population, and you want to do that for the 18 regions of Spain. Either you can write the code 18 times, or you can use a list, and do it all at once. And finally, I will also showcase this example in which we have two different lists, one with the statistical data and another with the spatial data, and how we can combine this to create a phased map that you have, I think, in the folder. You have the final image, in which we have an image of Barcelona in 3 different points in time, computing the same indicator, but you need to be aware that the 3 shapefiles are different because the number of census tracts each year in Barcelona it was different. So I needed to create a list with the 3 objects. So if you are ready, I change to I leave the presentation, I go to my R, so please open your R. You will see that I'm not sure if you are familiar with this tide log function, very nice, not function, library, very nice library that will give us a report of whatever things we do using tidyverse. And this is, aside of being just nice, is really helpful when you work with lists, because imagine that you will iterate the same process over the n elements of your list. And it could be possible that there is some sort of problem with a particular data frame or a particular object or a particular vector. And this tidy log will help you to track if, in case there is any sort of error, to detect in which particular element of the list is that error. So let's run some code here. Here I will create 2 data frames, data frame 1 and data frame 2. Basically, this is a toy data example in which, let me show you data frame 1. This is the structure of the data I'm working with now. I have an ID for the household. Then I have an individual ID for each person of the household. I have the age, I have the sex, and I have the country aside among other variables that I have. No, so in this data frame for country A, we are working, let's say, with just two families, no, family 01 and family 02, and in data frame 2, again, we have two different families, but one is composed by one single person. No, so imagine that these days I'm concerned about, for example, computing this average household size by country. No, and you know that the average household size comes from the number of people living in each household divided by the total number of households in a particular area. So let me come back to my code. So basically, we have our two data frames, and we can put them together into a list using the function list. No, we have our object here. We can inspect this object. We see that it's composed by data frames. We can call one of the particular objects also from here. You see that in the console, we are having this two square bracket thing. So I'm accessing the data frame 1, and I'm accessing the data frame 2. And now I want to set a name, because here I have 1 and 2, and I want to set a name to the objects of this list, so I can use the function names, define my names. Of course, you need to have the same number of names as elements. If not, some of them will keep the index. And now let's say that we have everything ready. We have a toy data example with a list of 2 data frames, and we want to perform iteratively this computation of the average household size. So remember that I have my data frame, and I see here, now I can see that the household 1 is composed by 4 people, and the household 2 is composed by 6 people, but I have this information as a variable, no? And this will be very helpful for me for computing this indicator. So basically here we are in the atomic structure of a list. Now you see that I will create a new list called df list2, and I will apply over my previous object df list, and I will define a function, meaning data frame. In this case, it will iterate over all the elements of this list. In this case, this is a list just of statistical data of data frames. No? And I can use the function of tidyverse add count by applying this to my variable ID household. This will set the count of people that is living in each of these households. No? So if I now call the object that I have in data frame 1, you see that we have exactly the same information, but I have a repetition of numbers telling me, okay, in household 01, we have 4 people, and in household 02, we have 6 people. Nothing strange. So basically now we can go to compute this average household size with this toy data example. No? And for doing that, I will first need to group my data by country, and I will summarize, creating a new variable called average household size, in which basically this will be, you see that my new column is called n, so I will take the sum of the unique values of n, so this means basically 6 plus 4, and I will divide it by the length of unique IDs of households. So this will give me the number of households in this fictional country. Let's say in this case, it will be equal to 2. So I will create a new object just for you to see step by step how this works. So I will create a new object, a new list object called df list3. I will apply over list 2, where I have my new column N, and I will apply this, which is, you see that is exactly the same structure as if you are working with just one data frame. So for me, the truly nice thing about Lapply is that helps me to be absolutely sure of the task that I'm performing. When I get into using loops or nested loops, sometimes for me it's tricky to clearly follow what is happening inside. So basically, if I run this, I have now a third element composed by two objects, one for country E and one for country B. And if I call it, you see that I have now this indicator about the average household size being in the country A equal to 5 and in the country 2 equal to 1.5 because there were two households, one with two persons and the other with just one. So, of course, once you get to this situation where you have what you were expecting to get, you need to get this information out of the list. And we saw before that you can do it basically using the double bracket by calling each of the elements, but it could be also the case, like it is my case, that you want to wrap all this information together in a single data frame. And for doing this, you can use this combination of do-call and rbind functions to row bind the different elements into a single data frame. And if I run this code, you see that now I have a new data frame in my environment called aggregate database with two observations and two variables. And so basically now we are getting in the form of a data frame the result of the process that we were doing. So far, so good. Okay, so before I was creating different elements in my console just for keep the track of the different steps. But of course, you can perform all this at once, no? And if you have your original list, you can apply the different steps all at once, and this will basically create the same and will give us the same result. So very clean way of working, very easy to understand what is happening inside the Laplace function, and very convenient, either if you need to work computing the same whatever indicator you need for different countries or for the same country in different years. No, for example, not bringing this to our field of social science. So example number one, simple showcase of how to create a list, apply some function over the different data frames, and get the results out of that list into the data frame. Example number two, we want to create, and I think you have it in the folder of today, I put the images, no? We want to create a graph like this, no? I don't like this graph, but it's just for a matter of the example. We have the evolution of the population in each region of Spain, dividing the bar according to where people were born. Either they were born in Spain, or like me, they're migrants in Spain and they were born outside but live in different. And so we want to create these 18 different graphs at once, no? And we can do that using this list. So let me clean my environment so for keeping it clear. So basically I want to read some data. If you open the data, basically the data that we have here is population counts by municipality of Spain. No, of course, municipalities belongs to a province, and provinces belongs to a region. Com is for autonomous community, that we call it here. No, and basically the rest of the columns you have is we have this data for different years, and we have population counts according to where people were born. No, so this means population born in Spain, population born in Latin America and Western Europe, Eastern Europe, Africa, Asia, and others. No, so this is our original data. But we want to arrive to this output, which is this graph by region and basically comparing Spanish-born versus all foreign groups. Okay, so first of all, we need to, let's say, manipulate this data in the sense that first, we want to compute, well, I'm computing here the total population, but we don't need it for this. Okay, yes, we need it. I'm first computing the total population, because recall that I have the population counts, the population Spanish, Latin America, Western, but I have no the total population. So I'm computing first the total population living in each municipality in each year of Spain. Basically, then I need the population. X is a population foreign-born population, no X is for extranjero in Spanish, sorry. And I can take this basically from my previous column of population total minus the population born in Spain. This will give us the total number of the foreign-born population. But because this data is now by municipalities and we want to have this by regions, we need to group this data by year and region and basically summarize the information that we want to visualize. So here is the Spanish-born population, which will be equal to the sum of the population Spanish, and the foreign-born population, which will be equal to the pop X that we compute in two lines before. And also you are familiar that if we want to move this to a ggplot environment, well, we also need to move this data from the wide to the long format. No? So this is what I'm doing here in the last line. So if we run this chunk of code, you see that now from the original data, we move to a much shorter data frame. This is because now all the municipalities belonging to the same region are grouped. No? So basically now I have data for year 2000. We can put it like this. So year 2000 Andalusia, Spanish-born population, year 2000 Andalusia, foreign-born population, year 2001 Andalusia, and so on and so forth for the 18 different regions of Spain. So now it's where we want to move this data frame to a list environment in order to work iteratively with it. So if you have a data frame and you want to create a list from that data frame, you can always split that data frame by a particular variable. No? So basically, in this case, I want to split the data frame regions by region, sorry for the names. So I will create a new object. I will call it out for output, where I will split regions. And using this argument, I will say, okay, I want that each element of my list is one of the regions of Spain. So if I run this, I get a list with the 17 elements inside. I know that Spain is composed by 17 autonomous communities or regions, so this looks correct. And if you see this, you see that you already have the name. You created a named list directly. And then basically you have the same structure for all, because we have the same years for all the data. So we have 34 rows for 4 different columns. So this is the structure of each of the elements that are inside in the data frame. So now we can also use this list strategy to create multiple ggplots at once. No? So this is what I will do here. I will create a new object. I will call it df list1. I will apply over my previous list called out, and I will define a function as df as being a single data frame for each of them. In this case, I'm adding this option shippen to 9999. This is for avoiding the scientific notation on the axis of my data frame. And then, as usual, as you are familiar to do, you will define a particular ggplot. No, in this case, it's a stacked bar ggplot. Nothing strange. I want to create a stacked bar, so I will use geometry bar, setting the position equal to stat. And I also will face it over my variable with the name of the region, because I want to have the letter with the name of the region. And the other is nothing more than aesthetics, no? The labels, the theme, and some particularities of the theme. So if we run this chunk of code here, you see that now we have the df list object And if you click inside and you call one of these, you will get in your viewer the image of that particular region. Okay? So this means that now you have a list with 17 ggplots inside done at once, no? Instead of using this code 17 times for creating the same type of plot, we put this inside the list and we can do that. Of course, once you, in this case, you don't only want to see your plots in your viewer, but you will also want to save these plots as an image. So here I'm setting my working directory for the folder called images. And again, using the apply, in this case, I'm not creating a new object because I want this to execute directly and to save this. So I will use the apply function over the names of my list, because the names, remember, is Andalusia, Catalonia, Aragon, and so on and so forth. And basically, I will use the ggSave function as usual, or I always use the ggSave function for saving my plots. I will use it as normally, but this will execute and produce the 17 different plots at once. It will take a couple of seconds, but okay, so once we have here, if you go to the folder, now you find that you have 18 different plots with the same structure, not the same type of plot, but one for each of the regions of Spain. So it's a way of exploring your data very fast and easy, and well, saves you, in general, all this list and apply thing for me, it's a time saver. So this was my second example that I want to share with you, creating multiple ggplot objects and saving them as an image. And the last example that I want to show with you here is the objective is this. I won't elaborate here about what the location quotient is. The location quotient is a spatial indicator that helps us to understand where a particular characteristic of the population is either overrepresented or underrepresented. So in this case, it's a division. So when values are equal to 1, this means that a particular census tract has the same value as the region of reference, in this case, the whole municipality of Barcelona. When values go below 1, means underrepresentation, and when values go above 1, means overrepresentation. So this is the first step for locating, for example, clusters of whatever thing. You first implement the location quotient, and depending on the results, you can think later to move, for example, to the local Moransai or whatever thing which is more fine, in terms of the statistics behind. So for this example, we need to work both with statistical data and with spatial data. So I will set here my working directory, and I will load some data and add the year because it was not included. I'm reading 3 different data frames that basically the data frames are more or less as we saw before, population counts of different types. But in this case, I have information for each census tract of Catalonia in a particular year. So also let me, for those of you who are not familiar with the spatial thing, in Spain, census tracts is the smallest spatial unit. A number of census tracts are inside a municipality, municipalities are inside provinces, and provinces are inside regions. So it's like four different levels of spatial aggregation. And in the case of Spain, and also in Switzerland, it's the same. The census tract is the smallest spatial unit for which you get aggregated statistics, in our case, about a population. But I also, because I want to create a map, I also need the shapefiles for creating these maps. So I need to read 3 different shapefiles. And again, be aware that we have different numbers for each year, because as I explained before, in Spain, the census tracts change more or less every year, because they are designed to contain more or less 2,000 people. So when one census tract grows so much that arrive to, let's say, 3,500, they split this census tract into two, and so on and so forth. So basically, we have 3 data frames with the statistical data, and we have 3 SF objects with shapefiles or the spatial information. Here you have a line just to see one of these particular spatial objects. In this case, this is the census tract division of Catalonia in the year 2000, just for you to follow what we are doing. So here we want to compute this location quotient, and also you know that aside of using functions in R, we can basically write our own functions, and this is a very simple one, so I prefer to write it and use mine than not to look for this function in some different part. So okay, so now we have these 3 different data frames on the one hand, and we have these 3 different spatial objects on the other hand, and we want to put them into different lists to work then over them iteratively. So I will create a data list object with the statistical data, and I will create a list object called shape list with the spatial data. So again, you can always see what you have in the same fashion as we did before. So now I need to perform a number of tasks again over my statistical data. No? And in particular, I want first to create a new column, which I will call code moon. This is code of municipality with 5 digits of the ID. No? So let me see. So you see the ID of a census tract is composed first by the 2 digits of the province, and then by the 3 digits of the municipality. So I want to have a new column with, in this case, 08001, no, nothing more than that. Then, because we have data, both spatial and statistical, for all Catalonia, we want to filter that data, the data that corresponds to the municipality of Barcelona. And again, we want to add a column with the total population in each census tract. Then we want finally to compute this location quotient over the Western European population. No? In this example, we are concerned about where in Barcelona Western Europeans are more concentrated in the city. No? And also we will need to create some nice intervals for the coral plate that we want to create. So I will, of course, we can do this at once, but I will do it step by step just to follow the logic. No? So I have my data list with my 3 elements for the 3 different years. I can check one of these, and I see that I have these population counts, and I have the year at the end. So now first, I want to add this code moon new variable. So if I run that line, you see that now we have 10 rows, and basically now I have a new column at the end. Sorry, this is because of how my view is. We have added for the 3 elements of our data frame, we have added that column to the 3 of them. And now we want first to filter the cases that corresponds to the municipality of Barcelona, and I know that the municipality code of Barcelona is this 08019, and we want to create a new column with the total population living in each census tract, and of course you can, this is just for being very clear of what I'm doing, no? Some in Spanish, Latin American, Western, and so on and so forth, no? And I want to force this is important because then we need to merge this with the spatial data. I want to force this to be a data frame, not this combination of table data frame, because they're kind of messy for when you want to connect them to spatial data. So nothing strange here, but you will see that, remember, for example, remember the number of rows of our data frames in this list object. And once I run this, you see that we have a much smaller number, because here each row is a census tract, and before we had the census tracts of all Catalonia, and now we only have the census tracts of the municipality of Barcelona. So now I can apply my function for computing the location quotient. I define a function with two arguments. Basically, the location quotient is a division of a particular population group over the total population. And as I said before, here we are concerned about the spatial distribution of the population born in Western European countries that lives in Barcelona in these 3 different years. So I can compute this, and I can check, and you will see that now you have a new column with the values of the location quotients in each of the elements of your list. And here I'm creating these, let's say, pretty intervals that I want to have for plotting my map. So you can use the if-else strategy or whatever other strategy. There are libraries for computing intervals, but I try to be here really clear of what's happening. So I will create a new variable. Sorry for the name, it was there, I didn't change it. So this will be the location quotient, that we can change this directly here. Or because it is for Western European categories, no? So if I apply this, now I have a problem. Okay. Sorry, because I need to change also this here and here, because you know that we are creating these intervals, but will order them alphabetically, or what it considered alphabetically with this. So I'm doing, first I'm creating the intervals, and then I'm using base R to order the levels of these factors. So I have the 0 on the top and the +3 on the bottom, no, nothing more than that. So now I can run this again and have no problem. So basically, the first part of this task is done. Now we have the statistical data. We computed this indicator of the location quotient. We have that for the 3 different years, and we subset the general data just to get the data of Barcelona. So done with the statistical part of it. So now we need to concern about the spatial part of this exercise. And again, here, using my list of shapefiles, I will perform a number of different tasks. No, I will create an ID with the number, the province. I will create an ID with the municipality and a general ID for the census tract. And once I have this, then I can put it together, and now I can subset my shapefiles of the whole Catalonia. No, I want just to keep those polygons, those census tracts that belong to the municipality of Barcelona. And this is what we are doing here. And here is where we arrive to this point in which we can combine elements of different lists, and also from lists with different element types inside, no? So we need to call the library pur, and I will create a new list object. I will call it list.com, in which, using the function map2, I want to put together, I want to, my first argument here are my shapefiles, because on my shapefile, I want to add the statistical data. So this is what I'm doing, this order. And then basically I will use a left join, telling that I want to merge or left join this data by the common variable, both in the statistical and in the spatial data, which is this ID of the census tract. That's what we were creating this before. Okay, so basically now we have in a single list the results, or the spatial and the statistical data together. But because, let me show you, because I want to retrieve a map tile for my map, I still need to do some task because of the coordinate reference system of my shapefiles. And when we want to retrieve a map tile, we need to move this to this flat project long lat. No, so nothing more kind of technical thing about working with maps, but we can transform the coordinate reference system of our three shapefiles at once, again, inside a list. And this is basically what I'm doing here. This line will change the coordinate reference system of the three different shapefiles at once. And now I want also to create a color palette. For this, I will use the R Color Grabber library, and I will create a 11 elements palette using the spectral palette. And also I want this gray color for the cases in which there's no data. Now, it could be possible, and I'm not sure if this was the case, but it could be possible that there was one census tract with not a single one Western European living in it. So basically, that's why I have the gray color. So now we have inside the list object called listcom, we have both the statistical and spatial information. And we can take this information out and put it in a single spatial data frame. No? And we can use, as I show in my presentation, the combination of the do-call and rbind function. So I will create this data frame final. If you open this, you see that this is an SF object, which means you have a statistical data, but you have this particular column of geometry with the definition of the boundaries of the census tracts of Barcelona. So because I want to retrieve a map tile, I need to get the bounding box, the area in which Barcelona is placed. And I can take the bounding box of any of my three different maps of Barcelona in 3 different years, because maybe the distribution of census tracts inside change year by year, but the general definition of the Barcelona, it doesn't change. So I will use the first element of my listcom, remember where I have my shapefiles inside, to get the bounding box, and I will create this bounding box, and this is just a technique for getting the margins of the map tile. So I'm adjusting the left, right, bottom, and top margins of the image I will retrieve, and then using the library ggmap, I can get a toner lit map tile coming from Stoner Maps using the function get statement maps. So if I run this, and I can call the object, and you see that basically I have now an image of Barcelona, and I will use this image to plot my 3 different maps in a facet map. So basically now we are outside of the list, because remember that we took out all the elements to this data frame final, and I can create, as usual, using the geometry SF function, I can create a facet map in which I will face it by my column year, because we want to have the 3 different maps of Barcelona with the different years. I'm setting the scale fill manual to use my own color palette, and the rest things here are just aesthetic parameters. So this is because of changing the name here to. Okay. So okay, now I can save. You have it in the folder. So basically, we arrived to this situation in which, by working with 2 lists of different types of statistical and spatial data, we were able, with very few lines, to create this facet map telling us where these Western Europeans are located, and you see that they are building, let's say, a cluster of concentration in which is the central part of Barcelona. For those of you who have been here, this is basically the Gothic Quarter, Eixample, and Gracia, no? And we can see the evolution of how these clusters evolve over time, no? And in blue and violet colors are the areas where we don't find, or we are this Western European population is underrepresented. So basically, these were my three different examples to, let's say, showcase what it can be possible to do with lists. Of course, I try to keep them to the most simple expression in order to be easy to follow, but you can apply the same structure to much more complex situations, no? And I truly expect that this will helps you saving a lot of time. So thanks for your attention. And if you want to ask some particular question, I'm here for that.
Hi, thank you. I'm sorry for the noise outside. I have to change place because the connection was bad. And maybe since I have a question about the way you using the lists, because in internet, I always see these two separation between people using the tidyverse ecosystem and at the same time, the person using the base way of using it. And especially for the case of list, it's always people tend to prefer per over the base and apply family. Because there is some advantages like the type system and the fact that it's really flexible. And what could be the argument for people to use the apply family, for instance? Because I still see some code where you have the S apply, L apply, and stuff like that.
This is coming to demographic terms. This is an age effect, no? I have been working with R for 10 years, so of course there was no tidyverse there. So first I learned base R, and now I'm using a lot of tidyverse because of course I acknowledge its capabilities and it's fantastic. So I remember once I heard this Hagley Wickman said, R is a language to get shit done. So I have no opinion. Sometimes if you see my code in general today, I was trying to use all the time the tidyverse approach to R to keep it clear, also because I was expecting a younger audience than me, so base R sometimes is tricky. But I mix it because of what I remember first. No, so I have no opinion about if it's better or worse to use pur versus the apply families. If you are familiar with one of them and you know how to use them, well, then you can choose whatever you want. I always tell my students that general knowledge of base R is not necessarily a bad thing. On the contrary, it's a super good thing because it helps you to understand the inside process of other functions. And sometimes where there's no function that helps you doing what you want, well, you can use a lot of base R to solve your own problems, no? And it's not like it has no dependency on other libraries. So I think it's a matter of age. No, I see now all students, they are all into tidyverse and they are very efficient using tidyverse and they know all the functions. No? But sometimes there are some problems that cannot be solved within the tidyverse environment, or they can be solved. No? It's more tricky or more difficult. And then base R can help you. So this apply family of functions will come from base R. Well, maybe they are growing old, but they are still very efficient. No, and I love the apply function. I love it. You know? And also, when I first met the pur library and this way, because before was kind of more tricky and difficult to combine elements of different lists together, but now it's very straightforward.
Thank you for your response.
If there are no more questions, here in Spain it's time for lunch. I imagine that in Switzerland you already had lunch before, but
I might have a question as well, also in terms of preferences. You mentioned the difference between data frame and table. So if you have a new project, what would you care to do everything on table? Would you try to do everything on data frames, or wouldn't you care at all?
No. In fact, these days I'm caring a lot because I'm working with this huge amount of data. So size was a problem, no? And I read it and talking with some friends. The table is, let's say fastly is a light data frame, no, which keeps the more minimum things that you need this to work. So, for example, in this project of the co-residence, in the creation of the co-residence database, the first step in my code before getting into the list and computing the indicator is moving from data frames to table data frames. So why? Because the amount of data is so big and my computer is good, but it's not a supercomputer. Huh? So I managed to get lighter list, no, at the end. Because when I work with that project, my memory here goes to the top, and I need to close Google. Sometimes I need just to run around and not touch my computer because it's on the extreme of its capacity. And I found that the table helps me making elements lighter. So now I'm using them a lot. But the only problem that that's why I referred before, is that I don't truly know the technical explanation why. But the table data frame are problematic when you want to merge them with spatial data frames, like maps. I truly don't understand exactly why, but I saw or I found that when the statistical data was a table, there was an error and things were not working. But just forcing that table to be just a simple data frame, the problem got solved. So that's why I was before talking about this changing from one to a. But I think tables are great, and in particular in the case where you have tons of data, it will help the processing process.
Thank you.
Great.
Last thing, but like when you say that you have way too much data into like your RAM memory, but why don't you put it like in an SQL server or anything to work with it with data?
No, of course.
Instead of having everything loaded every time.
It's a matter
Sorry,
of.
I didn't hear.
Yeah, it's here kind of strange, but I think I understood your question. It's a matter of data infrastructures. Not today, for example, this week I will receive a new super server that will put here in CED, in the Center for Demographic Studies, where I will be able to run all this process in this server with tons of megabytes of RAM memory, and it will. But for the last 6 months, I needed to push this project and I needed to work on my computer, personal computer. So yes, of course, you can move also to create a SQL database and work from that. But for me, it was important because the data was coming from so many different sources. And I imagine I'm working with 171 countries, I think. So for me, what's important to have all at the same time to make some checks in general to see that all the steps that I was performing were moving in the correct direction. So, but I think my workflow with this project will change a lot in the next couple of weeks just because of having a new server where I can connect directly to work with R inside that server, and this will help me a lot. No? The other day I was in a reunion with the director of the supercomputer center here in Barcelona, just talking about that, because now we are compiling and putting this data and creating these indicators, but the goal in the medium term, like let's say 1 year, is to run a worldwide multi-level model, no? And of course, I cannot do that with my computer. I'm not sure if that will be able to do with the new server, but I'm pretty confident that the supercomputer in Barcelona And so we are starting to make the connections to see how they need my data in order to then process it there. But it's a problem of infrastructures, no? Of the laptops you have, of the servers you have where you work, things like that.
Yeah, okay. Cool. Thanks.